This is for an ideal solenoid for if I'm dealing with more reality, the fact that it's a finite length, that's where that formula comes from. Take equation 3. Oops. I went to the wrong one. There we go, equation 6. Equation 6 comes from the reality of the fact that it's a finite length. And I believe I did a video where I derived it. All right, so we have a magnetic field going through a solenoid, thus the creation of an electromagnet. However, we were more concerned yesterday with the induction of creating a current from a changing magnetic flux, and so we were looking at the point where we turned it on and turned it off. That's why we can flip the switch there. I know that an EMF is going to be produced if I have a change in the magnetic flux with respect to time, which is just going to be dVA dt. And unlike the problems that we had just done, my area is not changing. I assume that you did not notice that that coil was getting bigger or smaller as you flipped on and off the switch. This time area is constant times dV dt. And my magnetic field times d dt of mu naught n I. U naught, constant permeability of free space. N is the coil density, which you'll calculate at some point. And what we're left with is di dt. So as long as I have a current that is changing, which you do when you turn on and off, you are going to get an induced current. Now, in the case of the solenoid just by itself, it does induce a current in itself. It wants to slow down, so as the current suddenly increases, it's going to create a secondary current in itself, which wants to slow down the increase in the magnetic flux. When you turn it off, it creates a secondary current in itself, which tries to boost up the collapsing magnetic field. However, we did not test that. What we tested is we had a second set of wires here. We had, and not going to do that again, I hope. Let's go for tan. We had a secondary set of wires inside here. And so this changing magnetic flux is affecting the second set of wires. And because the second set of wires is creating this, as experiencing a change in the magnetic flux within it, we're going to induce a current in that. That's what you were measuring at the very end. So that's the background behind the ladder. Questions to hear? There's 2 directions I want to go in now. All right, let's talk about AC current. Because if I go the other route, I'm just going to want to keep going. For the first couple of years, I skipped AC current because once we had 4 Maxwell's equations, we then go into and derive the speed of light, which leads very nicely to relativity. However, the student left the program here, went to NC State to be an engineer, and said it really would have been nice had you done AC circuits. And so I put AC circuits in.
Is this a new chapter?
All right, so in terms of chapters, see, chapter 30 was just magnets. Chapter 31 was Gauss's law for magnetism, Ampere's law. The derivation of the magnetic field on the VSOR would have been chapter 30. Chapter 32 was Lenz's law, so this is primarily chapter 32 we've done. And chapter 33 is AC circuits and inductors. No, we hit the basics, not gonna jump. So we'll do simple AC circuit stuff enough so that hopefully what you do on Monday will make some more sense. And then next Wednesday, probably jump back and hit a couple topics that I skipped over. I'm going to go over two methods for solving AC circuits. One of which is the phasor method, which is I guess it's a geometric way of presenting this information, and then we'll get into complex numbers. A phasor looks a lot like a vector, but it's more specifically, it is a vector, so it has a particular direction and a length. The direction is constantly changing, but the phasor is, the tail of the phasor is fixed, and it rotates around in the classic positive direction from a math point of view at some angular speed omega, or with an angular frequency of omega. So just imagine an arrow spinning around counterclockwise. If you picture the shadow, and so if I had a light up here as this thing is going spinning around, if you picture that there's a shadow on the horizontal axis that starts out here, gets smaller, then goes out here, and the length goes that far, and then it's smaller, then comes out here. And so the shadow length is oscillating back and forth. The length of the shadow is going to be what is known as the instantaneous value. And the length of this is the amplitude. That's the maximum length the shadow can be, is that when this is horizontal, so the length is the amplitude. Of the phasor. When dealing with AC circuits, traditionally capital letters are used for the amplitude and lowercase letters are used for the instantaneous value. So you might have an equation of, actually, and traditionally you don't write the deltas in front. So the voltage from the power supply is equal to some amplitude times the cosine of omega t plus phi, for example. This is the maximum value of voltage, omega is the angular frequency, and phi is the phase shift. Even though we will deal with a lot of problems where the phase shift is zero, reality is phase shifts rarely are zero. The current would be I, some maximum value of I times the cosine of, well, times some trig function, not necessarily going to be cosine. We'll get to that. So let's take a simple circuit. I have an AC power supply. This is the symbol used for AC power. Because current is alternating back and forth and voltage is alternating back and forth, you present it with a sine wave there. And into it, I'm putting a resistor. This has some maximum value of epsilon naught with an angular frequency of omega.
So why does that B have like a thing on it?
To indicate that it's a lowercase, it's how I differentiate, one way to differentiate lowercase from uppercase.
So that, is that voltage or?
That's voltage.
Okay.
Probably went a little bit too much on the flare there, but it's a lowercase v, however you write it. So if I can write the voltage of the power supply as such, well, I know whatever potential gains I have across here, I'm gonna lose across my resistor. Or looking at it, if I'm going from this spot at the bottom to this spot at the top, whichever path I take, I'm gonna have the same voltage potential difference between the two as I go across. So in my case of a resistor circuit, or an R circuit, this would also be the voltage of the resistor. So if I did a phasor diagram, it is incredibly boring. The fact that I have a phasor, and some textbooks will draw them just generically on the x-axis or on the horizontal axis. I tend to like the first quadrant. This would be VPS, which I could write that as epsilon sub naught, and V sub R. So that is the voltage phasor. The two voltage phasors, they're right on top of each other, they're equal to each other. That represents this incredibly complex AC circuit. This phasor is spinning around at some, I guess it spins at an angular speed of omega, or has an angular frequency of omega. Now, I know that V equals IR, that my potential drop across here has got to be equal to, so the voltage across the resistor has got to be equal to the current across the resistor times the resistance. So this would be epsilon sub naught cosine omega t plus phi is equal to I, the current across the resistor, times R. And so I times R is equal to epsilon naught over R cosine of omega t plus phi. So when expressed in terms of cosine, it's completely in phase with it's completely in phase with these two phasors. So I would draw my current phasor right over top of that. So for a more stark look, but apparently, this will do. And so I would draw my current phasor. I tend to draw the second one shorter than the first one. They're two different units, so they're different sizes, different scales. And so this is current for the resistor, and which is also the current coming out of the power supply. I know, it's nothing earth-shattering there. The cool stuff comes up in just a moment. All right, a lesson to take from this. For a resistor, the current phasor is in phase, in sync, in phase with the voltage phasor. Why this is important will come in. Questions to hear? All right, let's do a C circuit. In other words, a capacitor. I have my AC power supply. I have a capacitor. Same reasoning as before, the voltage from the power supply is gonna be equal to the voltage from the capacitor as I go from one spot to the next. This is epsilon sub naught cosine omega t plus phi is equal to the voltage from the capacitor. Well, I know that V is Q over C. My voltage is the charge divided by the capacitance. So that's going to be little q over my capacitance. So the charge on the capacitor is epsilon sub naught C. Actually, there's a right fraction there. Epsilon sub naught C cosine of omega t plus phi. So that would be the charge on the capacitor. However, I'm more interested in the current. If that's equal to Q, what does I equal? How do you find the current if you know the charge?
Q over dt.
Or
dq.
calculus version,
dq over dt.
dq dt. Which equals? So what's the derivative of Q with respect to time?
The current.
Keep going. Derivative of a trig function, come on. I believe in you.
Negative sign. So epsilon naught C, negative sign, or you already have that, negative sign of omega t plus phi times omega.
Yes. So if I graph that, if I graph my two functions there, my voltage graph is a cosine curve, so my voltage will look something like that. My current is a negative sine curve, so it looks like that, more or less. So when time starts, my current, the orange is current. When it starts, my current is at 0, and then some time later, my voltage becomes 0. So the current is leading the voltage. And so for a capacitor, current phasor leads the voltage phasor by pi over 2. Now, as we're talking about voltage here, voltage and EMF is an ideal voltage. So electrical engineers seem to have taken this idea of voltage, they want to use EMF. At some point, EMF, doing an epsilon was not particularly simple to do in creating books, and so electrical engineers decided to just use the letter E because it's not used enough for the voltage. So you will sometimes, or sometimes I've seen E equals IR, that's just the EMF as opposed to the electric field strength or the energy. The reason I say this is that when we're dealing with a capacitor, the current leads, so the current comes first, and then the EMF comes second. It's a memory thing. So, for a capacitor, the current leads the EMF, or the voltage. Now, it turns out, I'm just gonna sort of a sneak preview here, the man who brings the ice man, actually has a name. His name is Eli. Eli the Iceman. For this, the inductor, which we'll get to, the current, the voltage leads the current by 90 degrees. But that'll probably be next week.
So on the phasor diagram, would it just be, on the opposite side?
All right, so first off, we'll just do, we got epsilon sub naught and V sub C. The current leads, and so by pi over 2, so my current phasor would be over here. That's also my PS.
That's the 90 degrees.
So,
90 degrees.
yes, that is 90 degrees. That is supposed to be 90 degrees. Notice this right here is the amplitude of my current phasor. So that's just I, what we'll label as I sub C. So I have I sub C is equal to epsilon naught C omega. I'm going to divide both sides by C omega and switch the order around. So I have epsilon sub naught is equal to I sub C over C omega. Or let me write it slightly differently, I sub C times 1 over, I think I prefer omega first, omega C.